attention. Mrs. Najoua Kamoun, General Director of the National Institute of Research and Physico-Chemical Analysis, you have the floor.
Thank you. Good morning. At first time, I want to thank the organizer committee to invite me and to permit me to present the National Institute of Physico-Chemical Analysis that I am General Director. Our institute is located at the Ariana city. The institute was created by the law number 95 of January. It's specified in this section to the mission of the institute. The first one is develop and organize analytical tools in the country. The second one is provide to company, technical and scientific institution the means for performance, research, development and training in the field of physico-chemical analysis. It was designed to be a documentation center in terms of physico-chemical analysis, a technical service center to maintain, repair scientific equipment used by INRAP, assistance to other agencies, implementation of scientific arrangements, an institute of research and development, and a training center. What about human, material, and logiciel device? It is our center here. Scientific equipment with estimated value in the order of $15 million. For the human, we have about 32 researchers, 32% engineers. For technicians, it's about 37%. For workers, is in the order of 32%. And for student researchers, it's about 5%. INRAP has 170 public function workers. Total area of our institute is in the order of 3 hectares, which 6,000 meters square of covered area. For equipment here, we have a few of our equipments. Here we have separation technique for liquid, HPLC for gas also. Here we have a technique for inorganic elements analysis, a technique for atomic absorption spectrometry, atomic emission spectrometry, GC high resolution MS, GC-MS, and liquid C-MS-MS. Infrared Fourier transform, UV visible spectroscopy, X-fluorescence, environmental scanning electron microscopy, thermal analysis ATD, ATG, and DSC. Analytical equipment of INRAP, we have also XRD analysis, organic elemental analysis like carbon, hydrogen, nitrogen, oxygen, and sulfur. Ionic chromatography, water analysis lab. We have also GC-MS-MS, LC-MS, the principle is demonstrated here. We have also an NMR equipment worked at 500 megahertz. We have 3 researcher labs. The first one is called Laboratory of Analytical and Technical Method. It has 2 projects. The first one, watch normative. The second one is metrology. And the third one is tools and methods of analysis. The second lab is called Useful Materials Laboratory. It has 2 research programs. The first one, nanostructured materials, and the second one, valuation of minerals and rare earths. We have a researcher about metal hybrids, accumulator like nickel, metal, hydrogen, fuel cell, application, high performance cutting tools. The third laboratory is called Laboratory of Natural Substances. It has 2 programs. The first one, bioactive substances of natural origin. The second one is the biology, polymers, and formulations. Now, permit me to talk a little about physics condensed matter laboratory that I am a head at the Faculty of Science at the University of Tunis Al-Manar. I will talk about my research field. It was done with collaboration between the Institute of Electronics in south of France at the University of Montpellier too. My work is called Synthesis and Characterization of Low-Cost Nanomaterials Used in Photovoltaic Devices. For growth, the nanomaterials, we have choose low-cost technique to synthesize nanomaterials used in solar cell devices. What about these nanomaterials? At the first time, we can talk about renewable energies. It can come from geothermal, from the wind, from the plant growth, from the waterfalls, and from the photovoltaic cell. Our work is answered in this field. The first technique to grow nanomaterials is chemical bath deposition. We called it CBD. By this technique, we have already ground indium sulfide, zinc sulfide, lead sulfide, tin sulfide, copper sulfide. About these materials, we have already done 5 co-tutelle theses. We have already done 2 projects between our lab and the University of Tunis Al-Manar, and we have another project, IUF. What about this technique? Here we have a cell. It put it on the water bath. The cell should contain the chemical element that can combine to give the desired material. Our sample is put vertically here. Here we have thermometer to control temperature. We have heated magnetic agitator. The nature of the growth can be, the mode can be atom by atom. It can be also by agglomeration of clusters, and it can be by the combination of these 2 mechanisms. For the studies of effect of alumina doping on the physical properties of indium sulfide, our results have been already published in Journal of Materials Science recently. Here we have presented the transmission spectra of indium sulfide deposited on glass substrate and tin oxide substrates. In the 2 cases, we can see that we have high transmission in the visible range. Another thing, for doping with 4 atom%, we have the highest transmission in the visible range for both substrates, glass and tin oxide. For the effect of tin doping on the physical properties of thin films indium sulfide, our results have been published in the Journal of Materials Science. And for the influence of heat treatment on the structural, optical, and electrical properties of indium sulfide chemically synthesized have been published in the Journal of Renewable and Sustainable Energies. Here we have another materials. It's the indium oxide materials. We doped it with fluoride. It has a subject of the Tuniso-Algerian project for these 2 years. Here we can see we have for all our samples high transmission coefficient in the visible range, and the intrinsic transition between the valence and the conduction band shifts a little when we vary the atomic % of dopant. We can see the fluorine-doped indium oxide thin films have a high optical transmittance in the order of 80%. The optical band gap is 3.17 electron volt for undoped material, and it is in the order of 3.24 electron volt for doped material with fluorine. Then we can conclude that this material can be used as optical window in photovoltaic devices. Here we present the TSC curves. It is the thermally stimulated current. That here we can see the current of doped material is practically constant. That can conclude there is no trap in our materials. The second technique to growth nanomaterials is spin coating technique. What is the principle of this method? We have solution. We put a fine drop of the solution. After, we put the substrate here, and we turn the table. We can control the speed, the acceleration, and with a programmable spinner. Here we have polythiophane material. It's organic material that can be used like optical window in solar cell devices. We can see a high transmission in the order of 90% in the visible range, and the optical band gap is in the order of 2.3 electron volts, both for the glass substrate and glass coated by tin oxide. We can see here the presence of oscillation. It can be explained by the high homogeneity and uniform thickness of our sample. Here we talk about ternary material that can be used as absorber in solar cell devices. This material is ground by the third technique called chemical spray. What is the principle of this technique? Here we put our solution. By using a peristaltic pump, the solution arrives onto the nozzle. By using a compressed gas, the solution is projected onto the heated and cleaned substrate. And after that, we have parameters to optimize, like the height between the nozzle and the substrate, the temperature of the substrates, the time of the substrate. After here, we have plotted alpha h nu square with energy of photon incident. We can see that by varying the concentration of dopant in our spray solution, we can vary the optical band gap of absorber material. Then we can see for the inclusion equal to 10 atom%, we have an optical band gap in the order of 1.49 electron volt. This value is practically equal to the optimal value for optimal theoretical value for high conversion of sunlight to electrical energy. Here we have another materials, CZTS, copper, zinc, tin, sulfide material. It can be used like absorber material in solar cell devices. We have studied by XRD the space of this material, the spectra, and say that we have a casterid structure with the best crystallinity at the substrate temperature equal to 280 degrees. The band gap of this material is in the order of 1.53 electron volt. It is practically equal to the optimum value for the conversion of solar light. This material is the tin sulfide doped with indium. We have studied the structural analysis of, by XRD analysis of this material doped by different percentage of indium. Here we show the reflectance and transmittance spectra. We can say in the transparency region, we can see weak interference fringes, uniform thickness, as well as smooth surfaces. This material have a band gap for 6 atom%. Band gap is equal to 1.57 electron volts. The value is practically equal to the optimal one for highest conversion sunlight. As a conclusion, we can say we are able to realize different type of solar cell devices where the ohmic contact is tin oxide is ground in our lab by spray pyrolysis. The optical window can be zinc oxide doped with tin. It can be also indium oxide. It can be the organic material. For buffer layer, we have used indium sulfide. Also, we can use for buffer layer zinc sulfide. For absorber material, we have tin sulfide doped with copper, with indium. We have also doped it recently by silver. We have the ternary material or quaternary. It is the ternary CIS material doped with gallium and the CZTS material. After, I say thank you for your attention.
Thank you, Mrs. Kamoun. And then